So, hello everyone. Today our goal is to talk about local search algorithms, and I don't think I need to reiterate the importance of search. We have been doing this for the last many classes, and we have learnt that search is extremely important. It is a fundamental way to even think about solving a new problem. And to solve a new problem, we will first model it as a search problem and then apply one of our favorite search algorithms. And we have now done many search algorithms. If you go back, we have done at least 4 or 5 uninformed search algorithms, and we have done at least 4 or 5 informed search algorithms. So, we have done a lot of algorithms already, right. And those are good algorithms, but today I am going to talk about local search algorithms, which is a different way to think about search. And before I get started, as I always mention, I would mention that look, we stand on the shoulders of giants, and many of these slides and a lot of the material that I have learned has been due to some of the stalwarts in the field, and in this particular case, that the slides that I will use have been developed by Stuart Russell and used in Berkeley, and Subbarao Kambhampati at Arizona State, and Dan Weld and many other folks at University of Washington. So, what exactly is local search, and why are we going to study this, and what is so special about it, right. So, this is the goal for today. So, when you think of the word local search in the modern day and age, right, we think about something like this, right. Tell me all restaurants near IIT, right, or as this says, what exactly is local search. So, when in doubt, consult Google, of course, this is the rule in life these days. And local search, it says, is any search aimed at finding something within a specific geographical area, right. Notice that this notion of local search is relatively modern, right. This happened in the last 10, 15, 20 years. Google itself came into being in 1998. So, probably not more than 20 years. I do not know if this notion of local search was present in this form in the previous generation of non-internet enabled systems. But we are talking about local search that has been around for the last 50 years at least. So, definitely we are not talking about this. I am not going to teach you how to do local search in Google. I am not going to teach you how to get the right restaurants or the right attractions near a certain location. This is not what we are going to talk about. We are going to talk about general search algorithms, where any problem can be formulated as a search problem and then solved using one algorithm, one search algorithm called the local search algorithm. Or actually, it is not one algorithm, it is a set of algorithms, it is a family of algorithms, and we will talk about what this family means. In this lecture series, we will end up probably talking about 20 algorithms, and it is okay, because you will understand them quickly. They are all sort of brothers and sisters of each other. Okay. So, up until now, so there are some differences in the way we have formulated the problem earlier, and we are going to formulate it now. In the previous set of lectures, the solution to our problem was a path to a goal. You have a start state, you have a goal state or many goal states, and your solution was to find what sequence of actions can I apply so that I can go from the start state to a goal state. A state was some partial information about the search that we have done so far. That was sort of what the state was representing, or at least the node was representing. State may be more than that, but at least that is what the node was representing. And we would do a relatively systematic exploration of the search space. Of course, we also talked about some algorithms which are not systematic, like iterative deepening search, but we also realized that while they are quote unquote not systematic, they are mimicking a systematic algorithm in a memory efficient way, right. So, internally principally what is going on is some kind of a systematic exploration, so that once I have explored a subtree, I can go to a different subtree and so on and so forth. We are going to turn things around completely in local search, and this is a fundamental difference. We will now be in a setting where not the path, but the state itself is the solution. Okay. Another way of saying this is that we are going to search in solution space. Each search node would be a solution. a good solution, a bad solution, but it will be a solution. In the worst case, you can return it and get some credit for it. And why is this useful? It is useful because in many situations paths are actually irrelevant. If you think about the n queens problem, just to remind you what is the n queens problem, I have to put n queens on the board such that no pair of queens is attacking. Now, in this situation, how did we model it as a search problem in the previous lecture slides? Does anybody remember? What was my start state? Empty board, very good. And what was each action? Add one queen, very good. And what was my goal test? All the queens have been placed and no two queens are attacking each other. Everybody with me? This is how we modeled it and there is nothing wrong with it. But notice what this was trying to do, it was trying to find the shortest path to a goal. Now, of course, in this case we know that all goals reside at length n, at depth n. So, it does not matter, as soon as we find the first we will stop, etc., etc. But really, it really did not matter whether I place the queen number 1 first in the first column or queen in the second column first. In fact, we can even do a better job of search by imposing an ordering in which we place the queens, if you want to do this, and we will get to that in the next set of slides. But for now, we really recognize that look, we are not really interested in a path per se. We are only interested in that final state which satisfies all our constraints. Where should the queens be placed in that final state, right? And we do not know that final state, that is what we are looking for. These kinds of problems are really well modeled as local search problems. So, you can use depth first search, branch and bound or IDA star or anything like that, but you can also use local search methods for these problems and they will often end up being faster in practice, as I will show you soon. Okay. So, let us there is one other thing that I want to talk about. Up until now we had been looking at satisfaction problems. Satisfaction problems is I want to find a path to the goal, and then once I find it I want to find the best path to the goal. So, there is some optimization going on here also. But suppose I am only interested in find me a path to the goal, that is what I am going to call a satisfaction problem, right. I am just interested in making sure that all my constraints are satisfied. It does not matter whether it is the most optimal way to satisfy them or not. On the other hand, there will be some optimization problems like find me the optimal path to the goal or optimize some objective function in general. And notice now that I am sort of doing this, at the back of your mind, if some people know gradient descent, they can start thinking about gradient descent. If some people know backpropagation, they can start thinking about backpropagation. If some people know any other optimization framework, you can start thinking about those. Now, what is a harder problem, satisfaction or optimization? Optimization. So, actually if you go into the theory of Turing machines and so on and so forth, if you do a complexity course, you will find that by and large all satisfaction and optimization problems sit in the same complexity class. Let us see if we can convert a satisfaction problem into the optimization problem. I have some constraints and I want to satisfy all such constraints. Can I cast it into an optimization framework? How? Let us say I give you a set of constraints C1 to Cn and my goal was to find a state which satisfies all of them. On the other hand, now I am interested in an optimization problem. Can I cast this original problem into an optimization framework? For optimization I have to minimize something. What will I minimize? Cost. What will be the cost here? Oh, total cost for an operation, I do not understand. Number of constraints satisfied, very good, very simple. Just minimize the number of constraints satisfied. Oh, maximize the number of constraints satisfied, or minimize the number of constraints which are not satisfied. And if you have got to 0 in this minimization problem, then you have found a solution to the satisfaction problem. If you have optimized it to that level, and if you still can't find, that means the constraints cannot be satisfied. That is also a possibility. So, really any constraint satisfaction problem can be written as an optimization problem by just saying minimize the total of number of constraints which are not satisfied. Now, going back in the other direction is slightly more tricky, but not that much more tricky. For example, if I give you an optimization problem where I say minimize an optimization function subject to some constraints, if I want to send it back to the satisfaction world, what would I have to say? So, in the satisfaction world, we have to say find a solution that satisfies all constraints, but now we have an objective function that we want to minimize or maximize, let us say maximize. Now, you have to write it down, I do not want an algorithm. So, this is one major learning in AI that I am hoping you would get. I mean, I have been trying to instill it again and again. Please, when I say formulate this problem as the other, do not think of an algorithm, do not think of an algorithm. Please think of the modeling. Does that make sense? Model a problem as the other means whatever inputs this algorithm needs, you change the inputs of the first problem in the format that the other problem is able to take it, the other algorithm is able to take it, the other formulation is able to take it. Okay? So, I am interested in formulating an optimization problem as a satisfaction problem. In satisfaction, I am given just a number of constraints. In optimization, I am given a number of constraints and an objective function. So, what do I do? Which cost? The optimization cost is maximum, that is the constraint. So, yeah, possibly, or you could say something like this, you can add a constraint that objective function less than equal to C or greater than equal to C if I am in the maximization world. If I get a solution, repeat with objective function greater than equal to C prime, which is greater than C, and do some search in the constraint setting and try to solve several satisfaction problems leading to the answer to the optimization problem with arbitrary closeness. You can do that. And in practice, what people have found, not in practice, in theory, what people have found is that most optimization problems, when converted to satisfaction problems, are in the same complexity class. So, really we can assume that satisfaction problems and optimization problems are not very different from each other, they are sort of equally difficult or equally easy more often than not. You can still, yeah. So, question is if optimization cost is in the real domain, what do you do? So, you can get to arbitrary closeness. You can keep doing binary search in that real space and keep asking the satisfaction function if you have a solution or not. And the more number of times you ask that question, the more number of times you would be able to see that where the exact optimality is, and at some point you will find the right solution. Complexity will not change very much, because in practice you will not need to do too many satisfaction calls, right. Again, you can have strategies like you can double the optimization cost and you do binary search in that space and so on and so forth. So, there are tricks of the trade which we can employ to model an optimization problem as a satisfaction problem. Nobody does that in practice, again this is more of a theoretical exercise, but it can be done. Okay. So, for example, a constraint satisfaction problem that we are going to study next in the next set of lectures would be a goal satisfaction problem, a satisfaction problem, but then there are equivalent constraint optimization problems which are which have constraints. In addition, they also have an objective function. And now, if somebody knows neural networks, what is the training procedure? Okay, most people do not know neural networks. Training procedure is an objective optimization problem. Subject to the constraints of the network, what is the meaning of a parameter, what function each thing is computing, optimize the objective function for me. The objective function could be fit as closely to training data as possible. So, all this deep learning business that people go crazy about, at the core of it, it is an optimization problem. However, in the class that we are studying today, we are not going to talk about those kinds of optimization problems very much. because those kinds of optimization problems are continuous optimization problems. Optimizations where your variables are real valued, because the parameters are real valued. However, in this class today, we are going to talk about discrete optimization problems. Optimization problems where the variables are discrete, not continuous. So, ILP, integer linear program, can be thought of as an optimization problem that we can solve, but linear program we will not solve, because that is a different set of techniques. Although at one level abstraction they will be similar, that is the beauty of it, and we will touch on that towards the very end of the class. Okay. So, with that background, where are we? So, we are now in a setting where my problem is an optimization problem, and the solution of the problem is a state. These are the two constraints that are needed to apply local search. And of course, if you think a little bit deeper, then if you really want paths as a solution, then what will you do as a state? Your state would be many paths. See, you can always convert a systematic problem into a local search formulation. We are saying state is the solution, so let me search in the path space. If I can search in the path space, then I would be able to apply local search there. So, if you did not get that, it is okay, it is not a big deal, but the point I am trying to make is anything that you could have done earlier, you can do now in the local search version also. Okay. And we will be interested in the optimization problem. So, as soon as we look at a state, we should be able to say that this state has this much objective function. So, we have an objective function black box given to us, where we put in a state, a solution, a good solution, a bad solution, and it tells me how bad it is or how good it is, what is the value of the objective function. This is the setting we are in. Okay. So, and just to give you a heads up of where we are heading, local search is this mechanism which only keeps track of a single state, does not worry about everything else, how it reached there, etc., etc., etc. It just worries about the single state, and it moves to neighboring states, which is why it is called local search. You are searching in the local neighborhood. And what is local neighborhood? We will talk about it. And the advantages of this procedure would be that it will use very little memory, and moreover it will scale really well in practice. Okay. No guarantees more often than not, but it will be able to find reasonable solutions in large or even infinite state spaces. As we said, these are pure optimization problems. All states have an objective function. The goal is to find the state with the maximum or minimum objective function. It does not really quite fit into the path cost goal state formulation, although path cost goal state can be converted into a local search formulation, and technically you can convert a local search formulation into a path cost goal state formulation, though it may not be most effective, and local search really does well on these problems. So, we can go back and forth, but the formulation that we have is given a state, given a neighborhood of a state, given an objective function which evaluates a state, find me the state which has the highest or the lowest value of the objective function. Okay. We will continue from here in the next section.